Greetings, the Astro 30 here, and this is part 2 of this speaker protector design. Now, I made some changes in the interim, and I just want to explain why this low ESR capacitor decided to start venting. Well, it's the actual design of this circuit. Now, if we remember, with this DC detector circuit here, this transistor, when it's turned on, is going to allow the negative voltage from the power supply to come up through the collector across the positive of that cap. Now, because this cap is sitting at half voltage potential at the 0 volt rail, that's effectively now reverse polarity on that cap. We're now applying negative to the positive. And this is a virtual earth, technically speaking, so what we're doing is we're now reverse charging that capacitor. And an electrolytic capacitor is not going to like that. Now, this was before I actually added some drain resistors, bleed resistors on the input caps, because the input caps would hold a charge for a fairly long time, allowing it in the DC detect state, holding it in that state, which was putting a reverse charge on the capacitor. The way to fix that is, well, put the bleed resistors in and also change the electrolytic capacitor to a non-polarized. And just so everybody knows, a non-polarized capacitor will charge in either direction and it doesn't care. And the circuit still works the same. The other change was I changed the 47K resistor in the RC network there to 100K, so it gives me around about a 5-second turn on delay. So if I just turn my load on, which is now at 27.2 volt, it's a good 5 seconds before the relay engages, which is okay. But however, I'm currently measuring the voltage across that non-polarized capacitor, and we're sitting at around about 18 volt. So if I now apply DC to the input to put it into protect mode, we can see we have a good -4 volt there going across the capacitor. Now, if I take one of my inputs and put it to, say, the negative voltage rail, we have now a good -8 volts across that capacitor. So without those bleed resistors on the input, it was holding, well, anywhere between 5 and, in this case, nearly 10 volt across the capacitor in the reverse direction, hence why it was about to vent. Now, what would happen if this circuit was in constant DC detect mode and it was holding it in the DC detection state and, you know, not allowing the relays to turn on because there's an amplifier fault? Well, what's eventually going to happen to this capacitor? Well, it's going to explode. So what I'm going to do, just for demonstration purposes, is I'm going to apply about maybe 5 or 8 volts in the reverse polarity direction across that capacitor. Let's face it, the capacitor's already stuffed. Okay, I've got my supply set at 8 volt roughly. And that's pretty much what happens. Oh, that stinks. Wasn't as spectacular as I wanted it to be, but yeah. So you can imagine that if that was actually in the speaker protector unit and it was detecting like -30 volt DC across that cap, that capacitor won't last very long at all. So using a non-polarized capacitor in this instance would be a very good idea. So that actually vented in a very controlled manner. So this is basic electronics 101. If you see a capacitor that's starting to bulge like that, that capacitor is pretty much done for. The electrolytic inside the, or so it should say the electrolyte inside the capacitor has started to boil to the point where it's drying it out. And that's the reason why most switch mode power supplies stop working, is because of bulging capacitors. Now, when you want to intentionally blow up a capacitor, it doesn't want to know. So, just for shits and giggles, why don't we actually overvolt a capacitor and blow it up for the hell of it? So I've got a 220 microfarad 16 volt capacitor with the supply cables connected the correct way around, and I'm going to apply 30 volts up it. Now, this won't take long at all. Well, that was not spectacular. So I've got a 470 microfarad capacitor, 16 volt. I'm going to put 30 volt up it. This is the last capacitor I'm going to sacrifice. Here we go. That's pretty much what happens. So, word to the wise, always check polarity, always check voltage ratings, don't exceed either, and you should have a working circuit. Now, that being said, that 63 volt 100 microfarad capacitor sitting there experienced a similar event across its pins there, because it was also held in reverse polarity for quite a fair amount of time. However, it hasn't started to vent yet, but it would have started drying the electrolyte out. So I'm just going to do a quick check with a known working capacitor of the same value, same type, same voltage, just to make sure that the capacitor is still within ESR specs, we'll say. So we'll use this crappy tester device here. I'll just bend that out of the way so we can see the LCD. Put it under a test. It says testing. We have an ESR of 0.87 ohm, and it reckons it's an 88.88 microfarad, which is a loss of 6%. So I've got the known good capacitor installed, so let's do the test. Now that says it's got an ESR, equivalent series resistance, of 0.53 ohm, and it's roughly 90.64 microfarad. So that's a good indication that that other capacitor is starting to dry out, or pretty close to it, but also at the same time it's still relatively in the ballpark of good. Do I trust it and want to use it in a circuit? Probably not, so I'll buy a new one. So just so I know that this capacitor's been through hell and back, I'm just going to put a little blue mark on the top of it so I know not to use him in any important circuit. Okay, I've made some modifications to the circuit. You may notice now that there's a 100 microfarad electrolytic capacitor now in place of that bipolar one. I've got the meter up across the capacitor. So now when I bring, say, the input to the negative rail, we can see it drops down to 0 volt thereabouts. All of about 15 millivolt there, which is fine. It's now no longer going in the negative. I was also wrong when I said the 559 and 549 BC transistors there had higher base emitter and collector emitter voltages. They don't. The 547 actually can handle 45 volt at the base and emitter junction, and something like 60 volt between the collector and emitter. In the past 5 minutes, several BC547 transistors, I mean, you look at this one here, I've completely blown the back of it off. I don't even know where that went. See how one pin's come off, which is laying at funny angles to it, and the back is missing completely. It just went, and that was the end of that transistor. I was experimenting with the LED light there to make the circuit simpler, and put, I believe it was the full 27 volt into the base, and it didn't like it. So we'll ignore the 4.7s here for a minute and this LED, because I blew that up trying to experiment with the light circuit. We have two shorted BC549s between the base and the emitter junctions, and two fried 10 ohm resistors. Those other two transistors of BC547s that I just moved out the way, they're also shorted between the base and the emitter junctions when I was mucking around with the indicator circuit. Now, how did I fry those four components there, the two resistors and two transistors? Well, I took this input lead and I took it down to the negative, and I held it there for about 10-15 seconds, and all of a sudden something started to smoke. Then it caught on fire almost. You could see it was glowing real red, and what was happening is the 10 ohm resistor here and the 10 ohm resistor over here in the AC loss detection circuit decided to fry. And the only reason they fry like that is because they're passing a shitload of current. So the only way in this circuit it could have been passing a shitload of current was something was being shorted, like one of the power rails was being shorted. So here's the original schematic, which I actually got all the whiteboard information from. This was drawn up in 2014. I can't remember why. I don't remember if I even tested it properly, but however, everything's the same. This transistor here, Q3, is the one that went shorted between the base and the emitter, and this, which is a 4R7 here, but it was a 10 ohm in the breadboard circuit here, fried. Now when that fried, I believe, because this transistor is switching up the negative 35 volt rail up into the offline, which is up here, and this electrolytic capacitor didn't like that, as we already previously mentioned, and for long periods of time that resistor didn't like it, because I believe with the negative coming up into here, it was going through this resistor, also going through this transistor, which is the second transistor it took out and shorted the base emitter junctions together, and also fried this resistor, which was also a 10 ohm resistor, because for some reason this circuit was being switched to ground at the time. So basically we were shorting out one of the power rails to ground, technically speaking. That's what I surmise happened there. So I've now changed the topology, because you'll notice the loss of AC detection circuit here only switches the ground, it doesn't switch the negative. So I've done away with switching the negative, albeit it's made it a little bit more complicated. It's added an extra transistor. Actually no, there's still 3 transistors in there, yeah. What I've done is I've changed it to 546s, which will be the final design, because they can handle a higher input voltage at the base and the collector, base emitter with open collector and collector emitter junctions respectively. So it's now been turned into a single-ended supply. Therefore you only need the positive voltage rail off the filter caps to make this work. Goes through this 100k resistor, which is into this transistor here, which is a PNP BC556, which is turning this into a switch. This is just the, well, basically the biasing resistor for this transistor, this 22k. which comes off of the collector of this BC546, which is essentially switching the ground, even though it's coming through this 22k resistor, switching the ground up through these two 22k resistors to turn this transistor on once this detects DC in either direction. We've got the negative part of the circuit being detected via the diode that has the cathode going to the input by bringing it into the emitter. If you remember from a previous speaker protector video, we used the emitter of a transistor in order to allow the negative DC flow through the collector emitter junctions. So this is basically the same thing. When this transistor switches on, after this one switches on, so both of these are switched on, this will allow through this 100k resistor to go into this third transistor here, which will also turn it on. Now this is also switching earth up through this emitter, through the collector, through the 10 ohm resistor, into the 100 microfarad capacitor and 100k resistor to the VCC line for the RC network. This diode provides a quick discharge path for this said capacitor. So when this transistor turns on, this is the offline now, which I haven't drawn in, but this is the offline, and when that transistor switches on, switches up ground through to here, it'll discharge this capacitor for a start and bring this offline down to ground potential. Now you may be saying to yourself, well, why didn't I do that here? Well, it wouldn't work properly, and because it's a PNP transistor, it's going to be switching the positive through, which is not going to work on the offline because the offline is already at positive potential. So we need to then put it through another NPN switch, basically inverter, to invert it so we're now switching the negative to still make this circuit work, and that was the multimeter turning off. And it's not as simplified as I wanted it to be, but I have gotten rid of the back-to-back PNP-NPN transistors and the need for the negative rail. The only thing the negative rail is doing is providing power for the loss of AC detection circuit, which in the real world and in the real circuit it won't be doing. So that's the changes to that circuit. Nothing else has changed apart from I've changed them to BC547s, and I've used all of them, routed about 5 of them, and had to order some more. So this is what happens when you design something and don't test it fully properly. And this is the very big reason why you always breadboard stuff, because like shorting out transistors or blowing up transistors or blowing up capacitors, or you know, burning out resistors, overcurrenting something, at least in here you may damage the breadboard a little bit by doing that, or blow an LED or whatever, but at least you can then sort the problem out with the circuit and actually make it work correctly, which is what I've done. So this saves time. Well, not necessarily time, because it takes time to then fault find what you've done wrong, but it saves the hassle of, okay, you've built the circuit, it works, okay, let's make a PCB for it. And you make the PCB and you send it off to, you know, mass production in China, for instance, to have all your PCBs made professionally. And they come back, you assemble it, and then you put it into rigorous testing after the fact of the preliminary design stage, and find, shit, resistors are starting to burn up, or capacitors are starting to vent and blow up for no reason. This is why you need to test, and I've gone through and voltage measured everywhere around the circuit just to make sure that everything is referenced to the ground of the circuit and not the negative, because A, that will kill the capacitor, and B, basically short the negative to ground, causing it to burn up resistors, because the 10 ohm resistors are actually the only thing preventing the two rails from shorting together, basically. And so the resistor is then acting as a fuse. A poor man's fuse, but it'll burn it up and then go open circuit, and then the circuit may no longer work, and in the process probably destroy a transistor, which it did. So this is the exact reason why we always breadboard and we test thoroughly and retest again, because there's nothing worse than making a circuit board and it doesn't work, or it doesn't work properly, or it blows up. See, it works with both positive and negative now. So if I hold the positive on the positive, sorry, the input on the positive, nothing is smoking, and I can just touch this resistor here. Nothing is hot, that one there. Nothing is hot. Transistors feel fine there. That one feels fine. Transistors feel fine there. So nothing is getting hot in the circuit, and it's still performing. And with the meter, with that taking it to positive again, so we've still got about 15 millivolts, almost close to zero. So just switching earth or switching ground, and then when you release it, it comes back up to around 18 volt, which is because of the 100k resistor. So yeah, that has fixed a few of the problems. I don't know what I was smoking when I designed that, because I basically took Rod Elliott's from ESP's input stage, which was similar like this, but he had, instead of down here, he had the a PNP transistor up here switching the positive instead into the offline, which would have then gone into basically what I've got on the whiteboard now, an NPN transistor to turn its base on, which would then turn the relays off. Now, it was still connected to negative, but because I was switching negative, that's completely different. He was switching positive, which was not going to do any damage to the rest of the circuit if it was laid out correctly. So it would have worked with bipolar if I hadn't messed around with it and changed it to negative. Now, I'm not sure why I changed it from the PNP up here to an NPN down here instead, except for the only reason I can think of was to eliminate an extra transistor, which was probably a bad idea. So you live and learn. So this circuit, as I displayed in part 1, does not work properly, and I would recommend not using it. So I've yet to draw up the complete circuit that has been corrected here with the changes, which will be done in the final part of this video. I hope there's only going to be 3 to this, where I'm going to actually make the circuit board, mount all the components and test it all. And I'm going to limit the design down to 2 relays, one DP-DT and one SB-DT, and it's going to be switching 2 left and right channels, or 1 left and right channel respectively, and a sub-base channel, so it'll be a 2.1 style speaker protector, so it can handle up to 3 amplifiers. And I'm also going to include the filter caps and power supply circuitry on the same board, so it will make it one complete power supply speaker protector unit rather than having 2 separate boards. And eventually we'll use that board for something, but for now it'll just be made up for the sake of making it up. Now, I'm waiting on an exposure box, UV exposure box from New South Wales, I believe it is. The ad description says it was designed for stencil art and stuff, but it's still photographic exposure, so it'll still work with PCBs just fine. And I believe from the photos that I saw, it also has a timer on the front of it, so you can actually rotate a knob and change the amount of time the exposure is on for. So that's handy. And I've also ordered some Kingston pre-sensitized PCB material plus developer again, and yeah, those should be able to expose within 60 to 90 seconds normally, and about 10 minutes under normal UV light, which is what I was doing before, which was using 15 minutes, which is extremely long time. So I'm probably going to go at the extreme end of the scale and go 90 seconds to expose the board. I've also ordered some tungsten drill bits for 0.8 of a millimeter, etc., so I can actually drill small holes. And this is also not just for this project, it's also for that sub-base controller project that I've got sitting on the floor, which I haven't worked on in a few days. So I can make up that mute PCB a lot easier. I was going to use the press and peel method for that. I decided, nah, I'm not going to do it that way. I'm going to expose it and then just cut and drill it like I used to do, because photo etch is a hell of a lot easier than trying to do direct etch, which is basically what press and peel is direct etch. Anyway, I'm waffling on about a different complete topic here that's not really related. So I'm going to end this video here and try and make sense of all this crap that I've been filming over the last couple of days and edit it down and together into a concise video for you and upload it as part 2 of designing a speaker protector, or designing a DC loudspeaker protector. And yeah, we'll see you in the next video or next part, whichever comes first. Anyway, I'm the Astro 30 saying I hope you enjoyed this video, and please remember to rate, comment and subscribe below. You can always follow me on Facebook and Twitter. The links are in the description as usual. Anyway, this is the Astro 30 saying see ya, and try not blowing up too much, even though it's fun.